Okay, so we're talking about the sum and difference formulas. Kind of introduce the formulas just really quickly so you understood how the plus and minus signs work. Remember, you pair them, like whatever's on top pairs with what's on top, whatever's on bottom pairs with what's on bottom. So sometimes they match the signs and sometimes they mismatch the signs. We are going to do a few examples using the formulas, and then after those examples are done, we may have time where we'll do a proof of why the formulas are what they are, or at least one of the formulas. Okay, so as you progress in mathematics, you'll see more and more proofs for why things are the way they are. They're good for us to look at. Okay, I have that at the beginning here, but I'm going to skip that and we'll do that one at the end. Okay, let's use the formulas. So this is our top part of our foldable. It is the sign of u plus or minus v. If you look at that flap, that open door, and open it up and you've got that first example, the sine of pi over 12. So if I just asked you what the sine of pi over 12 was, would you immediately know the answer to that? No, because the sine of pi over 12 is not an angle on the unit circle, correct? So we can immediately recall sine, cosine, tangents, and reciprocals for things that are on the unit circle. So basically what we want to do is we want to think about, this is a sine of pi over 12. So we're going to be thinking about the sine of u plus or minus v. And we want our u and our v to be angles from the unit circle. Okay, so we want them to be angles from the unit circle. In which quadrant would pi over 12 be? In the first quadrant, right? It's much smaller than the first angle that we know, pi over 6. So here's what I would do. I would think about the angles that I do know in the first quadrant. And I could even list pi over 2, and I could keep going if I wanted to. But what I would do is I would think about them with denominators of 12. So I'm just going to make each one of those have a denominator of 12 by multiplying by the well-chosen one for whatever that fraction is. Here I would have 2 pi over 12, I would have 3 pi over 12, and I would have 4 pi over 12. Okay? So those are angles from the unit circle that I do know the sine, cosine, tangent, and reciprocal functions for, right? I could recall any of those without a calculator. Can you use any of those angles, adding them or subtracting them, to create an angle of pi over 12? Blake, you say yes. Which ones would you use? Sure. Pi over 3 minus pi over 4 would really be 4 pi over 12 minus 3 pi over 12, which is pi over 12. So what we're going to do is we're going to take this sine of pi over 12 and we're going to write it as the sine of pi over 3 minus the pi over 4. That is saying the same exact thing, sine of pi over 12. It's just written out so that it is a difference of two angles. And we're choosing angles that are actually from the unit circle. So, I don't immediately know the sine of pi over 3 minus pi over 4. But if I flip back to the front of my foldable and I look up my sum formula for sine, I can break that up. I could do the sine of u times the cosine of v plus the cosine of u times the sine of v. And so my u is pi over 3, and my v is pi over 4. Okay, so following that formula, I'm doing the sine of u times the cosine of v minus the cosine of u times the sine of v. Okay, that's what that formula says. And I will replace those u's and v's with my angles. The sine of pi over 3 times the cosine of pi over 4 minus the cosine of pi over 3 times the sine of pi over 4. Folded this one. You just need to make 2 quick cuts. Are we okay with how I did that in the formula? Now you just evaluate those things individually, knowing what you know about the unit circle. So remember I said unit circle doesn't go away. We still need to know the unit circle. Okay. So now I'm going to work it out. What is the sine of pi over 3? The sine of 60 degrees, which is on the unit circle, square root of 3 over 2. What is the cosine of pi over 4? Square root of 2 over 2 minus the cosine of pi over 3, which is 1/2, times the sine of pi over 4, which is square root of 2 over 2. And then I just have to follow PEMDAS. So I should multiply things first. In this first product, the square root of 3 times the square root of 2 in the numerators will be the square root of 6 all over 4, because you multiply your denominators. And then minus the square root of 2 over 4. So I took care of multiplication, and now I just have to do subtraction. They already have common denominators, so I just subtract in the numerator and keep my denominator. So I would have the square root of 6 minus the square root of 2 all over 4. Hello. Oh, wow, thank you. You guys have a good day. Happy Valentine's Day. That's as good as it's going to get for me, but there I have an exact value for pi over 12 without a calculator. If you type this into the calculator and then you change into radian modes, and you do sine of pi over 12, those decimals will be the same. Questions about that example? Anything that we did there? Okay, let's look at the next example. Now, in this example, over on the other side, I've got the formula's already been filled in. So I've got like sine of 120 times cosine 60 minus cosine 120 times sine 60. So when I see that formula, if you turn over to the front side of your foldable and you look at all three formulas, you know, clearly it's behind our sine formula, but it looks like the sine formula because the sine and the cosine are getting multiplied with each other instead of like cosine times cosine in the next flap. Okay. Now, I think on this one, maybe not the best example for us because you can do all of those angles on the unit circle, right? Like you can actually figure out what the sine of 120 is, what the sine of 60 is. But another way to do it is think about what this is in your formula, so condensing your formula. When it's written out like this, it's asking you really to do the sign of what as a sum or difference. 120 minus 60, because in this formula our signs match. So by writing out this formula, we are doing that sine of 120 minus 60, which when you think about that, that's just 60 degrees, right? So to me, it's a lot easier if I condense that using the formula. What is the sine of 60 degrees? The square root of 3 over 2. Now, you would get the same answer by doing all the work that we had done in the previous example, where you figure out, okay, what is the sine of 120? What is the cosine of 60? If you do that work, you should get the same answer, square root of 3 over 2. Okay? But this would be an example of where you could work smarter, not harder. If you recognize that their sum or difference is going to be a single angle on the unit circle, then condense that formula, and that's all you have to calculate. Now, if they added or subtracted and it wasn't an angle on the unit circle, then I would go through the work and actually figure that out. Any questions on that? Okay. Next flap is our cosines. Okay. So notice and kind of compare the flaps for sine and cosine. I'll have the formulas on the board tomorrow during your quiz, but still it's good for you to kind of like see like how are they similar, how are they different. And the flap for cosine, this is one where the signs will mismatch. So like if you're adding the two angles, then in the formula you're going to subtract the products. and vice versa. Also notice that when on the sign flap, you multiply in your products, you're doing like a sine times a cosine always. But when you're doing the cosine rules, it's like cosine times cosine, and sine times sine. So we want to do the cosine of theta plus 3 pi over 2. I'm just going to follow the formula. Okay? This is telling me the cosine of u plus v. So if I follow the formula, it says I should take the cosine of u times the cosine of v, and then use a minus sign. So I mismatched my positive and negative. And then I should do the sine of u times the sine of v. And we would just write these out with the u and the v in them. So I would say cosine theta times cosine 3 pi over 2 minus sine theta times sine 3 pi over 2. What can you evaluate in that expression? Do you know anything from that? Yeah, what could you evaluate from there? Just say it. You can do the cosine of 3 pi over 2. The cosine of 3 pi over 2 is the x-coordinate, which is 0. What else can you evaluate? The sine of 3 pi over 2, which is -1. Well, cosine times 0 is just 0, so I don't even really need to write that because I'm going to be adding. So this kind of goes away. It's just 0 plus something, or 0 minus something. And then I have negative sine theta times -1, which is, negative sine theta times -1 is positive sine theta. So the cosine of theta plus 3 pi over 2 is really just sine theta. That would be easier to do. Okay. Could you please, on the side next to this, work to verify the identity? So you see a left side, you see a right side. Which side is more complicated in the next example?
Right side.
Is more complicated?
Yes.
The left side is more complicated. Okay, the left side is more complicated. So could you please work on the left side using your formula? You might need to flip to the front of your flap, okay, to see the formula and use it. And you already know what the answer is. It is going to be another sine x. So see if you can verify that that's actually true. Put it into the formula and work it out. You are working out the left side of that equation. When it says verify, it's like the work that you did in type 2. You know what the answer is, you got to show the work to make it true. Since that was u minus v, when I look at the cosine formula for the difference of two angles, then I use a plus in between my products. So you should have cosine pi over 2 times cosine x plus sine pi over 2 times sine x, and that should equal sine x. And then you evaluate the trig functions that you know. So cosine of pi over 2 is 0, and sine of pi over 2 is 1. And then same thing happens, 0 times cosine is just going to be 0, so don't even really need to work with that. And then 1 times sine of x is sine of x. Remember how, like on the quiz corrections that you turned in, I want to see that final line where you actually show me the two things are equal, sine x equals sine x. I know it's true. You have just verified that. cofunction identity. So I gave you back in section 5.1 reciprocal identity, quotient identity, second identity, and we even talked about even odd identities. There are other identities called cofunction identities, and cofunctions are kind of like based on the left-right horizontal shifting of the graphs. When you shift a certain distance, cosine becomes sine, or sine becomes cosine. So that's what cofunction is all about. Okay, excellent. Do we have any questions so far that need to be addressed? Are we feeling pretty confident about this? You guys are so quiet today. The next ones are tangents. So tangent's probably like the most complicated formula, I guess, because it has like a numerator and a denominator. But remember that the formulas will be in front of you during the quiz and also for the test. So just make sure that you follow them. Okay? If you look at the front and you're doing the tangent formula, on the numerator you add or subtract the tangents, but you keep whatever sign you were originally working with. So we are doing u plus v. That means in the numerator I'm going to do the tangent of theta plus the tangent of 3 pi. Okay, so the formula has plus or minus for u plus v on the left, and then in the numerator it also has plus or minus, so you keep the sign. In the denominator, you're going to do 1 minus the product of the tangents because you use the opposite sign. It has minus plus in the denominator. So if I'm doing plus in the original, then I should have minus in the denominator. Minus tangent theta times tangent 3 pi. And then just like before, evaluate whatever you can. 3 pi is coterminal to what angle on the unit circle? Pi, which is over at 180 degrees, negative 1 comma 0. So the tangent for that is 0. Okay, so I'd be doing the tangent of theta plus 0 over 1 minus the tangent of theta times 0. So that's really just the tangent of theta over 1, or tangent theta. That would be 1 minus 0 in the denominator. Okay. Now, the next one, the last one, is a great one for us to look at together because it can get a little complicated in like the working out pieces. Okay. Thank you. I'm sorry, I'm reading people's Valentines. Okay. So it can get a little bit complicated in the working out piece. So we want to do that one before we leave. Tangent of 255. Do you know the tangent 255? No, not exactly, not without a calculator, because that's not an angle on the unit circle. So this kind of takes us back to our very first example. Can you come up with some angles that add to 255? That are on the unit circle? 210 and a 45 degree? 210 plus 45 is 255? Okay, so that will work. So we're going to write this out as the tangent of 210 plus 45. Did anybody have any other ideas there? There's not one right way to add up to 255. So this works. You could do like 225 and 30. You can try different methods to add to that value. Okay, so there's not just one right way to do it. Okay, so follow your tangent formula. That would be the tangent of 210 plus the tangent of 45 all over 1 minus the tangent of 210 times the tangent of 45. Okay. Evaluate, what is the tangent of 210? Something with a square root of 3. Square root 3. Square root 3 over 3. What's its reference angle? 210? 210 minus 180? 30 degrees. It's a 30-degree reference angle, so the tangent of 30 degrees would be square root 3 over 3. So I would agree with square root 3 over 3. Would it be positive or negative? In quadrant 3? The answer would be positive. So it's positive square root 3 over 3. And then what is my tangent of 45? 1. I'm doing 1 minus, and then I do the square root of 3 over 3 times 1, which can I just write minus the square root of 3 over 3? You okay with that? Do a little bit of work. Okay, now here's what I would do to work this out, make this look a little bit nicer. Number one, I've got stuff being added and or subtracted in the numerators and denominators. Let's condense those by doing the addition or subtraction. In order for me to be able to add square root 3 over 3 plus 1, I need common denominators. So this one is really like 3 over 3, isn't it? Okay, and same for this one. And that will allow me to keep the denominator of 3 and just do the addition and subtraction with the radical in the numerators. Okay, so this will be square root 3 plus 3 all over 3 in the numerator. And then divided by 3 minus square root 3 over 3 in the denominator. So I'm liking that in that instead of having all those separate pieces, I have condensed them in the numerator and the denominator. And now what might you do? Multiply by the reciprocal. Excellent. So I have a fraction divided by another fraction. So I'm going to multiply by the reciprocal. So I'm going to flip that bottom one. So that gets me, and I'm going to rewrite this addition using my commutative property just because I don't like writing that radical in front. You can keep writing it the same way if you want. 3 plus square root 3 over 3 minus square root 3. How do you feel about that answer? It's looking pretty good. My only issue would be radical in the denominator. So, do you know what we would do if we have 3 minus square root 3 in the denominator? Multiply by 3 plus square root 3. That's the conjugate. Multiply by conjugate here. And this is going to rationalize my denominator. So in the denominator, I'll have 9 minus 3, which will be 6. Okay, the 3 square root 3 and negative 3 square root 3 are going to cancel each other out. In the numerator, I'm going to have 9 plus 3, and then I'm also going to have a 3 square root 3 plus another 3 square root 3. So that would be 12 plus 6 square root 3s. Okay, you can certainly FOIL that out if necessary, right? Do all 4 terms and then combine like terms. And then all of these things reduced by a factor of 6. So I could write 2 plus square root 3. Okay, that's better. So like I said, that's a good one for us to look at together because it gets a little bit complicated. Any questions there? Yes? No.